Hey guys, let's talk about power. You recall from Physics 1 that power is defined as energy over time. You recall that energy is charge times voltage, right? Such that power is charge times voltage over time. Charge over time, you recall, is the definition of current, right? So power is current times voltage. So that is the big equation to remember. Should make a lot of sense that if you have some resistor with resistance R and some voltage drop V, some current I going through it, that the energy dissipation. So this is the rate of energy dissipation. And that should make a lot of sense. So the unit of power is energy per time. So it's the rate at which joules are transformed or dissipated per second through a resistor. Remember, a resistor is like a light bulb or a speaker, transforming this electrical energy into some other form, into light energy or sound, something else. So we measure the rate at which that energy is transformed or dissipated by watts. So it makes sense that the rate of energy depends on the rate of charge, current, but also the voltage drop, right? So if you have a larger voltage drop, you have a larger rate of energy, and if you have more current, you have more charge, you also have a larger rate of energy. So let's do some examples. So example number 1, let's say we have two resistors hooked up to a battery. This is example number 1. And one of them is resistance R, the other is resistance 2R. Let's say they're both light bulbs. Which is brightest? Well, you want to figure out the current through both of them. Remember, the current for series is the same current. And the voltage drop is V equals IR. So clearly, if this is voltage V1, this will be twice the voltage because it has twice the resistance given the same current. So this should make a lot of sense that if you have twice the resistance, it'll have twice the voltage drop. And look at this. The power depends on the current and the voltage. So here, the current is the same. So let's call this resistor 1 and resistor 2. The power of resistor 1 will be its current times its voltage. And the power of resistor 2 will be the same current plus twice the voltage. So therefore, look what we have. Let's find a cool color to circle this in. This guy's the brightest one. I don't know if that purple shows, but you will do a baby blue here. So notice how in series, the larger resistor has more voltage drop, but the same current. Understanding that is essential. I hope that analysis makes sense. and then using the equation here, current times voltage, to understand the energy dissipation rate. So that means this will be twice as bright as that one. Okay. Example number 2. If I put the same resistors in parallel, now which is brighter? Ooh. Still answering the same question, which is brightest? So here we notice that the voltage drop is the same for both. Remember that very important rule for parallel resistors, that they share the same voltage drop, like sharing height. So this one went down twice as much height as this one, but these both go the same height. V drop here, V drop here. So now you want to think, how's the current different? Which has more current? Well, I hope you understand that the current through this one is I, but since this is a lower resistance will have more current. So look what happened here. So if we look at the power of these two light bulbs, the current now is greater here given the same voltage. So look at that. So here the 2R was brightest, now here the R is brightest. Understanding what's happening with current here and voltage here, understanding what's current here and voltage here is everything. Combining it with the equation, you get here that this is twice as bright as this one. Cool. Example number 3. Say we have a 120 watt light bulb. What is its resistance? So notice how light bulbs are categorized by their wattage. But that's assuming that you are in the United States. In the United States, you plug a light bulb into the wall, it has a voltage of 120 volts. So 120 volts is standard USA wall socket voltage. So we're assuming 120 volts. So if you were to plug this light bulb into Europe, in Europe they have 240 volts. So they would shine brighter in Europe. It wouldn't be 120 watts. So what is constant in a light bulb is the resistance, and we can use this wattage to actually solve for the real resistance of the resistor in the light bulb. So how do we do that? Well, easy done. We know the power. We don't know the current. We can solve for the current, and we know the voltage. So clearly, the current is 1 amp, and then we can use V equals IR. Look how easy this is. This equation and this equation, 120 volts equals 1 amp times resistance. Resistance clearly is 120 ohms. Easy. If I have a dimmer light bulb, for instance a 40 watt light bulb, let's solve for the resistance of the 40 watt light bulb. Again, this is assuming 120 volts. So we do the same analysis. P equals current times voltage. Current is, careful here, 40 divided by 120 is a third. V equals IR. 120 volts is a third of an amp times R. Multiply by 3, we get 360 ohms. I hope that makes sense, that if you remember in the previous diagram, when we have parallel resistors, this guy was brightest. The smaller resistance is brighter. The larger resistance is dimmer. In series it's the opposite, but we hook our lines in our houses in parallel because if one of them cuts out, the other one doesn't cut out. But if we cut this one out, then it opens the whole circuit, and we have an open circuit. We don't have a closed circuit. So parallel is so much better. Because parallel preserves the voltage drop over all resistors and keeps it constant 120 over everything. So a higher resistance means less current, same voltage, less wattage. So we can solve for that resistance running backwards. I hope that makes sense. Bring any questions you have on Monday. We're going to practice this more on Monday. Be sure to do your homework and practice all this goodness. And I will see you then. Have a great weekend. Bye, guys.